Hello, my name is Sean, and it's 9 o'clock in Denmark, in Aalborg, and we'll be starting the webinar. Today I'll be talking about uncertainty quantification in operational model analysis, its theory and applications in ARTeMIS Modal. So first I'll go through some context on system identification and uncertainty quantification. Then I'll go through the system identification methods that we use for uncertainty quantification, and then I'll finish with the main topic of this webinar, which is uncertainty quantification. So this webinar has two main pillars. One is operational model analysis, and the other one is uncertainty quantification. So, and now I'll start with the former. In operational model analysis, we aim to estimate the model parameters of our structure directly based on data. Those data are measurements of the structural responses, for example, accelerations or velocities, observed by sensors in some discrete locations on a structure. Those measurements are often collected under operation conditions of the structure, for example, wind waves, traffic, or rotating machinery, which often poses some challenge to the system identification methods to estimate model parameters. Over the years, there were many methods made for operational model analysis, and here my purpose is not to go through all of them and outline all possibilities, but to focus on the mostly used and well-known methods in the community. So the first group of methods is based on picking the peaks of power spectral densities of output measurements, and they are called frequency domain decomposition methods. Then the second well-known group is based on fitting a common denominator polynomial to half power spectral densities. And the last group of methods is called are the system identification methods. And these methods were adapted to model analysis from the automatic control community. And there we can distinguish three main categories. The first one are the prediction error methods, which try to minimize the error between the measurements, which are our structural responses, and some system responses emulated by the model that we identify from data. The second group of methods are the covariance-driven realization methods, which identify the realization of our system from the covariance sequences of our output data. The last group of methods are time domain subspace identification methods. Those methods use some geometric projections of our output data matrices in order to identify the eigenstructure of the vibrating system. And on those methods, in general, covariance-driven and time domain subspace methods, I'll be focusing on this webinar. And that is because of several reasons. For example, subspace methods are direct and computationally efficient for output-only system identification. And that means that they don't require any minimization or optimization procedure. They just directly estimate the model parameters and the eigenstructure of our system. Their estimates are asymptotically unbiased, meaning that they converge to the true parameters at infinity. There is a well-developed uncertainty quantification schemes for the subspace-based methods, which is the main topic of this webinar. And the subspace-based methods, there's a common framework that wraps the subspace methods in identification and fault detection and isolation, which is also well known by the community and used in structural monitoring. In this context, there are several challenges related to using the subspace methods for operational model analysis. First is that those methods are parametric, meaning, and those parameters that are used for the identification, they characterize the dynamic behavior of our structure. The problem is that we don't know the exact number of those parameters, so and we need to choose it, and that relates to the true model order of the system identification methods. The second reason, which is also connected to the unknown model order, is the fact that along the true modes of the structure, which are structural modes in our case, we identify some purely mathematical modes or modes related to the noise excitation conditions, which result in spurious modes in model parameter estimates. And those need to be somehow filtered from our structural modes in order to interpret the data, which can be challenging. The second part of this webinar will be focused on uncertainty quantification. And here by uncertainty quantification, I mean quantifying the statistical uncertainty of the parameters that we estimate directly from data. This uncertainty stems from the fact that the data are of finite length and afflicted by noise. So the methods that we use to identify model parameters are yielding estimates that are also afflicted by noise and subjected to statistical errors. Those errors we can quantify directly from data by propagating the uncertainty of the measurement onto our parameter estimates. That allows us to derive the statistical distribution of our estimated parameters and, for example, derive the confidence intervals of our parameters, which I illustrate here on our toy example. Similar to operational modal analysis, there are several methods for uncertainty quantification, and here I focus on two well-known groups of methods. First are Monte Carlo-based methods, which rely on estimating the sampling distribution of our estimated parameters, for example, by estimating them multiple times from different data sets, which are empirical methods. Or some methods rely on resampling the data, so estimating the sampling distribution, our estimates of model parameters from the segments of data, and then computing the sampling distribution from those segments, estimates that correspond to the segments. Second group of methods are first-order perturbation methods that rely on and delta-based methods that rely on propagating the statistical uncertainty of our measurements onto our parameter estimates. And on those methods I'll be focusing today. So there are several challenges that relate to both Monte Carlo-based methods, but also to first-order perturbation-based methods. And the main challenge is that their numerical efficiency. So for Monte Carlo-based methods, we need to have many estimates to compute a reliable approximation of the sampling distribution of our parameters, which is exhaustive. And in first-order perturbation-based methods, computing the perturbations of our model parameter estimates can result in big matrices, which, for example, for mode shapes can be also difficult to compute and involve some heavy computations. So uncertainty quantification in operational modal analysis deals with estimating the statistical properties of model parameters directly from data. So, and that can be used for several reasons. For example, to quantify quality of our model parameter estimates, and this quality relates to the variance of different estimates of model parameters. Or it can be used for structural monitoring, for example, for model tracking or change detection, when we try to compare the different distributions of some damage-sensitive features and identify the changes between the distribution, which can tell us something about the damage in the structure. So to propagate the uncertainty, we need to have a consistent system identification method, and about that I'll be talking now. So we assume the linear time invariant model for our system, and which is described by the second-order differential equation of motion. So here MCK are a standard mass damping and stiffness matrices that linearly map the accelerations, velocities, and displacements into our inputs. the inputs are denoted as U. The calligraphic F matrix here maps the input locations to degrees of freedom of our structure, and vector U tilde are the inputs that are unknown and unmeasured, which can happen. The vector Y are outputs, matrices L, A, LV, and LD. They map the degrees of freedom of our mechanical system to the sensor positions, and V is the sensor noise. So this linear system can be also characterized by modes, which are frequencies, damping ratios, and mode shapes, which are the solution to the eigenvalue problem of MCK. So now the problem is that we have our input-output data or output data in context of operational modal analysis, and we'd like to compute the modal parameters of our system. The problem is that it's very hard to estimate the MCK directly from data, but still we like to estimate modal parameters. And for that we can use different modeling of our system. Namely, we can model it in a state space. So here the state space model, it transforms the second order differential equation of motion into two first order equations. So here we see a discrete time state space model, which consists of two equations. First, here, it is the state equation, which models the dynamic evolution of the states, which are denoted here xk. Those states, they relate to some physical properties of our system, which are displacements and velocities. And the second equation, output equation, it records the data, the responses at sensor positions. So there are several very important matrices that we'll be identifying from data. The first and utmost important is the state matrix that models the dynamic evolution of the states, and it's denoted as A here. The input matrix B acts on the inputs U, and it transforms the inputs to our internal states. The B tilde and U tilde are related to the unmeasured and unknown inputs. The observation matrix C maps the states to our sensor positions. The direct feed-through matrix D acts also on the inputs, and it's null unless we have acceleration responses. And similar to the state equation, the matrix D and U relate to the unmeasured inputs, and V is the output noise. So this discrete time state space model is in a general setting. We have both inputs, unmeasured inputs, noise, and outputs. In operational modal analysis context, we don't have measured inputs. All inputs are unknown and unmeasured, so the terms BU and DU they disappear and go to B tilde and B tilde U tilde and D tilde U tilde. So this is the discrete time output only state space model. And here we can see that the state matrix A and observation matrix C, they directly relate to the properties of our physical system, which are mass, stiffness, and damping. So the modal parameters of our system can be directly computed from the eigenvalues and eigenvectors of A and the observation matrix C. And that is the task of one of the tasks of the system identification. So in general, in the literature, the system identification methods are explained by linking the covariances between the output measurements in time to the state and observation matrices, and covariances of the output measurements and the states, also to those matrices. Here we'll choose an alternative way to explain it, which is also standard and well known, and we'll be trying to formalize the dynamic properties of our data matrices, which are computed, which consist of sequences of our outputs. So for that, let's consider a recursion of our states and of our outputs. The n plus p plus q is our total data length, and consider the states computed at time instant 1, 2, and 3, resulting in x2, x3, and x4, and also the data recursion done in a similar way. So here, for example, we can see that when we consider state x3, we have ax2 plus b tilde u tilde 2, and if we input x2 from the previous equation, we have a squared, and so on, resulting in quite long equations. And the same going for the output, recorded output. So now we'll be trying to link those output sequences to our state and observation matrices. But for that, we need to first define the data matrices. So let's define y plus and y minus, which are data matrices that contain the sequences of our output data, which are shown here. Those sequences would be linked directly to the properties of our state space system. And for that, we need to define the observability matrix, which contains the dynamics of the system, as you can see here, and a lower block triangle topless matrix that contains both the dynamics of the system, but also matrices that relate to the inputs, so d tilde and b tilde. Now the task would be to formalize relation between the data matrices that we know and the properties that we would like to identify. And this relation is very simple. It is just matrix manipulation. So here we see that our data matrices, they yield superposition of the observability matrix and the states, and the state sequences, the lower block triangle matrix, H tilde, and then data matrix of U tilde, and data matrix of the measurement noise. So now knowing that, we would like to identify our observability matrix. The problem is that we cannot directly identify it from, for example, y minus, because of all of the noise terms. So we need to do some manipulations in order to directly factorize the observability. And this is basically what is done in subspace identification. So here let's consider two well-known and standard stochastic subspace algorithms. One which is covariance-driven algorithm, and the other one which is orthogonal projection data-driven. So they both revolve around forming a so-called subspace matrix from the data sequences. So here I denoted for the covariance-driven algorithm as HCOV, and for the data-driven algorithm as HDAT. And for the covariance-driven algorithm, we simply multiply. So we can continue. So for the covariance-driven algorithm, we multiply, we basically compute the covariance matrix of our output data, which is y plus times y minus. And the idea for that is to eliminate the noise, basically. So here we just simply work on the relation between y plus and y minus, and assume that the future unmeasured and unknown inputs, u tilde, are uncorrelated with the past outputs, and also that the noise, data matrix of future noise, is also uncorrelated with the with our matrix of data matrix of the outputs. And that so when they are uncorrelated, they converge to zero at infinity, and this results in the fact that we can factorize the gamma from our subspace matrix HCO. So here on the left we can see gamma, and on the right we can see the controllability matrix that relates to the covariance-driven algorithm, which is basically covariance between the future states and then the data matrix of the past outputs. So going to the data-driven orthogonal projection algorithm, this revolves around projecting the past data matrix, Y minus, onto the row space of the future data matrix, which results in this projection. We can see that the first part is exactly the same as in the covariance-driven algorithm. So we can apply exactly the same procedure, which results in gamma and controllability matrix relating to the data-driven algorithm. And those two controllability matrices, as you can see, they contain some properties of dynamic properties of the system, but also some properties relating to the inputs. So now the task is to factorize gamma from our H, and that is done by using single value decomposition, which is truncated at the model order chosen by us. Then we recover A and C from gamma, which is super simple. And then we estimate the model parameters from A and C, which is also very straightforward. And for theoretical systems where we know the exact model order, the job is done. We have our model parameters. But that is not the case in practice, since we don't know the model order, and we still need to identify our model parameters. So what we do in practice is that we estimate the model parameters for an increasing model order, which results in many estimates of the model parameters. And then we try to cluster those model parameters that we estimate into groups that have the same properties, which we can then say that they belong to the same mode, which are called model alignments. So here we can see on those two figures, we can see a stabilization diagram of natural frequency on the left, where where the estimates of natural frequencies are computed for an increasing model order. They are stabilizing along some vertical lines, indicating that there are some stable modes there. And there are also some estimates which are completely scattered around this diagram, which correspond to the mathematical or noise modes. So now the difficulty would be to separate those stable modes from those scattering modes. And on the figure on the right, you can see a zoom on the first stable mode, which would be the first modal alignment. So yes, and let's see how it looks in ARTeMIS. So I'll just open ARTeMIS. Here it is, and I will show that on a fairly simple example of the plate that is tested in the laboratory, and maybe in general some introduction to ARTeMIS Modal. It is a software for model analysis, both experimental but also operational model analysis, and also for structure monitoring. So there are many model analysis techniques inside, both for experimental and operational. And today we'll be focusing on the data-driven subspace-based identification methods, which we went through in the slides. So let's see how our plate looks like. Here we can see the geometry of the plate with the 16 acceleration sensors attached. The measurements are already uploaded in the manage measurement task. So here we can see just simply time series of accelerations, which would be then analyzing for system identification. So, and that is done in prepared data. So first we need to compute our Hankel matrices and the observability matrices that we've been talking about in order to identify the model parameters. So, and all of that is done here. First we need to configure, for example, choose the model order. So we can enable the stochastic subspace identification first, and choose the model order 80, which should be okay, and don't scale the data with any measure, just analyze the roll time signals. There are several estimators for the data-driven stochastic subspace identification, and here the main difference between them is both the weighting of the observability matrix, which can result in slightly different model parameter estimates, and there's the difference between the UPC, which is called unweighted principal component, and then PC, which is principal component, which involves weighting the observability matrix with some weights. The UPCX is the method that stands for extended unweighted principal component and involves uncertain quantification. And that is something that we'll be looking at the end. So here, let's allow automatic SSI estimation and press run. So now everything is being computed. Here we can see a plot of the singular values of the power spectral density matrices that indicate where are the frequencies with the highest energy from all the measurements. And later on we'll be seeing if we can find any stable modes that are stabilizing along those frequencies. So here are the results. We see that there are 8 stable modes, which are here. Those modes are computed successively until model order 80, which is the maximum model order that we chose. And we can see that all of those estimates, they have slightly different values of damping ratios, different complexity of the mode shapes, slightly different frequency, which we can then see in the modal alignment window, which is chosen here. So let's look at it. So here we can see the modal alignments. So we can see the frequency of the first mode varies slightly, damping ratio varies slightly, and then the complexity varies slightly. But it is considered stable by some indicators that we use in ARTeMIS. So still, the problem remains that we don't know the variance of those parameters. Maybe some of the estimates, they have high variance, and then when we compute some global modes here, which now are just the mean of the frequency, damping ratios, and complexities, maybe they are somehow making this mean slightly to one side or the other side. But we can figure that out by computing the uncertainty and see how it looks like. So, but first we need to go through some theory. So let's do it. In order to motivate a bit, what is this uncertainty that we are quantifying exactly? We've prepared a simple simulation of a mechanical system. So this simulation is a simulation of 100,000 degrees wind turbine blade model, which is degrees of freedom wind turbine blade model, which is showed here. We performed this experiment in a Monte Carlo setup, where we simulate 1,000 data sets from this blade. We simulated with a sampling frequency of 100 Hz. Within this frequency range, there are 9 modes. And we record the output data with 4 biaxial acceleration sensors. So for each single data set, we estimate the modal parameters from this data set, that is natural frequencies, damping ratios, and mode shapes. So that this many parameters allows us to draw a histogram of the estimated parameters. So here on this figure, we can see the 4 histograms that corresponds to the first mode. So first natural frequency, first damping ratio, first component, real valued component of the mode shape, and first the imaginary part of the first mode shape, component of the first mode shape. So the main first observation from those histograms is the fact that they are all aligned on the true value of the parameter from the model, meaning that on average we are having a good estimate. But we can see that all those histograms all vary slightly and result in a distribution of parameters, which resemble the distribution. And for example, we can be unlucky, for example, for dumping ratio, and have this method of 0.8% when the true value is 1%. But the estimate is still considered as a good estimate. It's just applicable with the uncertainty related to the amount of data samples that we use for the estimation and the knowledge that we induce on our measurements. So the idea here is to estimate this statistical uncertainty and the variance of our estimates just based on one dataset, which would be very practical for practical applications. So we do that with uncertainty quantification, and there are two main tools in order to do that. First is that we need to define a propagation scheme, so what we will be propagating onto what exactly, and then the second tool will be later on. It is a little bit of maths, but it's not a difficult maths because it's mainly based on one statistical theorem, which is called central limit theorem, and first order Taylor expansion, which every engineer knows from school. First, the main point of this propagation framework is the fact that the data covariance sequences are mixing, and it can be proved that they are asymptotically Gaussian. So we can write a central limit theorem for them, which is written here. M here is the number of samples that we use to estimate those data covariances, R. So we can see that the centered estimate of the vectorized data covariance sequences, centered by its true value, is asymptotically Gaussian with zero mean and a covariance matrix sigma. So that is very, very important because now we can use some statistical theorems and first order Taylor expansion to propagate this covariance onto estimates of our model parameters. So, and for that, we need to have a consistent system identification scheme. Fortunately, we have subspace-based methods, which we went through in the previous slide. And we saw that both the covariance-driven methods and the data-driven methods, they relate to the data covariance sequences R. So let's say that we write a first-order Taylor expansion for either of them, and here I just denote the subspace matrix for the covariance-driven or data-driven algorithm as H. So let's write a first-order Taylor expansion of H, which is evaluated at its true value. Here, the sensitivity matrix J is a first-order derivative of our subspace matrix H with respect to data covariance sequences R. And O is the rest term of the Taylor expansion. Now let's denote the vectorized subspace matrix, the difference between the vectorized subspace matrix and its true value as delta H. And we can see that this delta H relates directly to the sensitivity matrix and the difference of covariance sequences, where the rest term asymptotically goes to zero. So this is also very important, because then the covariance matrix of our subspace matrix writes as the product of those deltas. And we can write a central limit theorem for H, which is stated here, where we can see that the covariance of H is depends on the sensitivity matrix and covariance of the covariance sequences R. So now we linked our subspace matrix H with covariance sequences R, and in particular we'll link the covariance matrix, and we can use the same scheme to link the sigma R to our covariances of the model parameter estimates, which we do next. The second main part of this framework is the computation of this sensitivity matrix J. And as I mentioned earlier, it's a first order derivative, but as you can imagine, it can be quite hard to make this derivative, for example, when we deal with matrices. So to derive matrix with respect to other matrix, this can be very tricky analytically. But fortunately, we have the first order perturbation framework, which allows us to write the total derivative of, for example, of matrix in a simple way. So here I prepared a small toy example where we have three matrices, A, B, C, and A is the product of B and C. So let's define a first order perturbation of A, which is vectorized, and we write it here. Vec delta A equals to vec delta BC. So with the chain rule, we have vec delta A equal to vec delta B times C plus B times delta C. Then with the properties of the Kronecker product, we want to factorize delta B on the right and delta C on the right. And this is done very easily with the properties of Kronecker products like here. And then we can define a global, from the two sensitivity matrix, JAB and JAC, a global matrix, which is sensitivity of our matrix A with respect to B and C like this. So the covariance of A is defined as the product of deltas and is linked directly to the covariance of B and C, which, for example, are our output covariance of our output covariance sequences, and the sensitivity matrix. So this is quite straightforward to estimate, but can be exhaustive doing so for all the chain of the system identification. So in the nutshell, this framework allows us to propagate the covariance of the output data covariances, which is Gaussian, to the estimates of our model parameters directly in order to derive their confidence intervals and to infer about the statistical distribution function. So going back to our histograms and recalling that those histograms were created from 1,000 estimates of each of the respective model parameters, we can estimate the distribution function of any of the estimate here corresponding to any of the 1,000 dataset and draw it centered around the true value of the model. So we can see that the spread of the histogram and then this distribution function, they are aligned. The distribution well approximates the variance of the histogram, meaning that with delta method and first order perturbation theory, we can estimate, we can derive the distribution function of our parameter estimates, which corresponds to this huge Monte Carlo simulation, which is super practical. So for the practical application, here we again have our stabilization diagram of natural frequencies. And this stabilization diagram, of course, corresponds to the Winterberg blade simulation that I explained earlier. So now we draw the 95% confidence intervals around each of the estimates, and we filter out those estimates that are varying too much. So we define some threshold for coefficient of variation of, for example, natural frequency, and the estimates that are above the threshold are discarded. And that results in a very clear stabilization diagrams where we can see that each of the natural frequency estimates for the many model orders align around some natural frequency, and we can define clearly our modal alignments. So the last problem is that we have all of those estimates, but we want to have only one estimate of natural frequency, damping ratio, and mode shape that would be easily interpretable. So for that, we can use the information about our modal alignment. And of course, there are many ways to achieve it. Here we know that all of the estimates inside are the valid estimate of model parameters, and we somehow need to merge them together in order to give some representative value of the group. So, and that is done with the uncertainty of global modes. So here we can see those model alignments in zoom for the first natural frequency and damping ratio, and for the last frequency and damping ratio. So we can see that all of those estimates, they slightly vary. They have, all of them, they have some confidence interval, both for frequency and damping ratios. And now the question is to merge them together. So we do that by simply weighting each of the estimates from the modal alignment with their covariance matrix, summing them up, and renormalizing with the global covariance, which is a sum. So we basically make a weighted mean for different modal orders to estimate our global modes. And we can show it in ARTeMIS, which we'll do in a second. So here we need first to enable the uncertainty quantification method, which is a UPCX. So we need to enable those two checkboxes for enabling UPCX and automatic estimation with UPCX. We press start. Now, since the previously data-driven stochastic subspace identification is done, now we just propagate the covariance sequences onto our model parameters estimates. So we compute first the covariance of our output covariances, and then propagate through the chain of system identification. And when that is done, we can see the results. So here we need to enable UPCX and see all the estimates. So this plate example is actually not very good example to show the spurious modes, because the data is good and identification is quite stable. But we have one or two noise modes here, where we can see that the confidence interval of the natural frequency is quite high. The damping also varies quite a lot, as indicated in the here in the figure. And when we inspect the model alignments more closely, we can see now that we have the confidence interval for each model parameter estimate. But we don't have one for complexity, and that is because we need to enable the estimation of the covariance of the mode shapes, which is done here. So now the covariance of the mode shape is computed, and we separated it because it takes, when we have hundreds of sensors on our structure, it can take a little bit of time. But it is done now, and we can see that we have also the confidence intervals of our complexity, which relates directly to mode shapes. We can also show a confidence ellipsoids between frequency and damping, which are enabled here in the frequency damping diagram, where we can see the frequency, global frequency of the first mode and the damping ratio, and its corresponding 95% confidence ellipsoid, which corresponds to bivariate Gaussian distribution, and it's 95% quantile. So we can show it for different modes, and of course the uncertainty is different for different model parameter estimates. So that will be about it regarding ARTeMIS and the webinar. So our next webinar would be on real-time testing in operational model analysis with ARTeMIS Modal, and it will be presented by Dr. Pelle Andersen on the 25th of November 2020. I thank you for your attention, and bye-bye.